So far, as we've been taking a look at circular motion, we've been concerning ourselves with uniform circular motion, which is where the object is going around in a circle at a constant speed. But what if it's not? We'll just look at a higher level overview here to get a bit of a feel for it. But if you remember, when we looked at acceleration, we saw that the radial component of acceleration is responsible for changing the direction of motion, and the tangential component of acceleration was responsible for changing the speed. So let's say that we've got an object going around a circle. So here is our velocity pointing tangential. Let's say we're speeding up. In this case, we will have components of the acceleration both radially and tangentially. Like so. So actually I will drop the vector signs there. So the net acceleration, using the parallelogram rule here, would be pointing ahead of the center of the circle. If you're slowing down, the tangential component of the acceleration would be pointing anti-parallel to the velocity. And that would mean that the acceleration would be pointing towards the back. Well, in order for this to happen, there had to have been forces involved. So in this case, the net force would have to point in the direction of the acceleration. And again, we would have to break that into a radial piece, which that would be equal to mv squared over r, and a tangential piece, which that would be equal to mr alpha, or ma, atangential. Which would be, so we could write this as mr omega squared. We're going to write that as mr alpha, if we prefer. So let's think about, to make this concrete, let's think about a case where, say, in a plane here, I've got a rod that is attached to a motor. So this is our motor going through the horizontal, and then in the horizontal plane, perpendicular to the motor shaft, we have a rod. We're spinning around like so. And at the end of this, we have a mass. Like so. So we're going around in some sort of a circle like that. And again, let's say we're picking up speed. So I want to ask you, what is providing the radial component, the centripetal force here? And what is providing the tangential force, the bit that's responsible for changing the speed? Pause, and we'll get back with you. All right, in both cases, it's the rod. So how's that going to work? Well, this turns out to be a case where Newton's first law of motion helps us out. So this mass here wants to go at a constant speed. Since the motor here is trying to change that, what will happen is that my rod will get a little bit longer, like so. And in its attempt to return back to its original shape, we'll be exerting an inward force, like so. But that isn't the whole story. As the motor picks up speed, in addition to the rod getting lengthened out, this bit will be turning fast. It will be turning at a higher angular speed than the bit out at the end here, just by a tiny bit. But that will be enough. Let me choose a more contrasty color here. Sorry about that. But that will be enough to actually cause the rod to have also bent backwards a bit. So this is greatly exaggerated. So again, it's trying to return back to its original shape, and in so doing, it's whipping it forward, providing the tangential piece. And this turns out to happen whenever we have any sort of rotation. So this is going to give rise to a slogan that we'll see more than once. And that is, there is no rotation without deformation. This rod got a tiny bit longer and it curved back a tiny little bit. It got longer in order to allow this mass to go around in a circle, and it curved back a bit in order to help, in order to speed up the motion of speed up the mass at the end of the rod. Now, it'll turn out that in practice, a lot of times you can pretend that this deformation didn't happen for computational purposes, but this is indeed physically what's happening. We'll pick up with this thought in the last of our videos here on two-dimensional dynamics. And that is with my rant about fictitious forces. So we'll see you in the next video.